Hi everyone, and welcome back to another AP Calculus video. Today we're going to talk about volume, and we need to remember how we started using integrals to find area in order to understand how we're going to use them here to find volume. So let's recall, if we have a function like this and we wanted to find the area under the curve, we would take and split it up into little rectangles. The width of each rectangle, we called it dx, and we said, well, our rectangles are getting infinitesimally thinner and smaller, but the area still exists, and it's dx, the change in x, times the y value, so length times height. And that's our rectangle. And we said if they are getting infinitesimally smaller, all we had to do was integrate f of x, because that's y, times dx. Well, this is base times height. And that was the area under the curve. That's how that integral worked, and we would go from point A to point B. Well, now we want volume, and so we're going to kind of think of it in the same way that we did area, in that we're going to be slicing now, instead of a two-dimensional shape, but a three-dimensional shape into little cuts. And if we can find the area of that cut and integrate it from point A to point B and multiply it by now length times width times height, then we can set up an integral to find the volume. And so here's our first example. We've got this parabola, and we're going to suppose that the base of a solid outlined by this curve from 0 to 4 is constructed by squares whose side length is the distance between the x-axis and the curve. So basically what's happening is, if you think about having this be the base of some shape, you've got these squares going from the x-axis to the curve, and the squares are standing up. So remember, a square, and I'm a terrible three-dimensional drawer, this square is standing up. So it's almost like it's pointing straight out at you from the screen. And everywhere that I have this square, the height of the square is determined by where it falls on the parabola. So remember, a square is the same, the base and the height are the same. So the idea here is that we've got this flat base with these shapes protruding. And the idea that I want to understand here is that these shapes, as they go up, they have an area. So the area of the square would be side times side. So we need to determine what the area of the square, or what the side length of this square is. And so if I look at where the square is, the side length runs the distance from the x-axis up to the curve. It's the same as our height. It's the y. It's the y function. It's the function itself. So the side of the square has a length of f of x. And no matter where the square is, it's still f of x, because it's going to be a different value depending on where it falls, but it's still always going to be that y value, that f of x, which means the area of the square is side times side. So it's f of x times f of x. It's base times height. Now, how does this help us find the volume? Well, let's think about this. We've got this solid that's admittedly difficult to visualize, made up of all these little square shapes. And so you have these squares, and they get progressively smaller as you get to the edges of the parabola. So picture very tall squares in the middle where the y value is the largest, and then as the y value approaches those x-intercepts, the squares get smaller, and so it traces down. So to find the area, or to find the volume, what we want to do is we're going to slice right along those squares. And if we continue to slice those squares into small boxes, well, the volume of that box would be side times side, and then times the height of the box, so the width that we cut that box to. And the width that we cut the box to, if we kind of sketch this in as being, you know, and again, I'm just a terrible sketcher, but suppose we make this a three-dimensional thing. Well, then it's, there we go, then it's, there we go. The width of this box, how wide it is a factor of the x-axis. And we can actually think of it as dx. In the same way that we found our rectangles and we added up the areas of the rectangle to find the area under curve, what we're going to do is we're going to break this into a bunch of little boxes. And we're going to find the volume of each box. So it's side times the width, so base times height times width. And this becomes my width, the dx. So if we slice them up into all these super duper thin three-dimensional boxes with a width of dx, it's going to be base times height times dx. And if we add all that up from point A to point B, then we use an integral symbol to represent that. Remember, the integral just means add it all up. So what we're going to do is we are going to add up from 0 to 4 the area of the square, which is f of x squared, times dx. So this is base times height, and then dx is your width. So length times height times width, or base times height times width, depending on how you learned it. And this is the idea. This is the integral. And we can do this for any shape. So it doesn't have to be a square. We can take the surface area of the square, or of a circle, or of a semicircle, or of a triangle, and if we take that surface area of the top of the triangle and multiply it by dx, that's going to give us the volume of that super thin slice, that three-dimensional slice. And if we just add them up, that's called integration. That's what integration is. So our basic formula ends up being like this. So from point A to point B, a of x represents the area, the surface area of the slice. Here we had a square, so it was side times side. It was f of x squared. And that's how we do our setup here, and that's how we're going to solve these problems that are just going to be sliced. We're just slicing it up, okay? So let's go ahead and evaluate and find our volume. So we're going to integrate from 0 to 4, and it's going to be negative x squared plus 4x squared dx. And sometimes these are calculator based and sometimes they're not. We'll go ahead and use a calculator today. And here we have our area. It's 34.133. So again, the idea is that we are slicing this into slices of shapes we can find the area of. So whether that's a super thin, I don't want to call it a cube, it's more like a box, a super thin box whose surface area and who the bases are squares. So it's just the area, the base times the height. Now, what if we had, instead of squares, triangles or semicircles? Well, then the surface area of the box would be a triangle. So you do 1/2 base times height, and then your width would always be that dx. Okay? If it was a semicircle, you'd do 1/2 of pi r squared. You'd have to figure out what the radius is, but you could find that little area. The width would be dx, and the idea is you integrate from A to B, the area function of whatever the shape is, times dx, that's your height. And when you add that all up, you get the volume of the solid. So this is all kind of what I've been saying, and this is kind of the thinking that we want to do. And it's that it's all related back to how we found the area of a curve where we slice it into rectangles. The difference now is that we're slicing into three-dimensional shapes and then finding each little volume and adding it up through integration. So let's take a look at a few more. Suppose we have the base of a solid formed by this graph, x equals y squared over 4, and the line x equals 3. So the first thing we need to do is make a sketch. The cross sections are perpendicular to the x-axis and they are semicircular discs. So, okay, what does this look like? Well, in order to graph, I need to solve this guy for y. So let me go ahead and do that. I'm going to have 4x equals y squared. So y equals the square root of 4x. Let's see. And it's going to be plus or minus. So essentially, here's what I have. I've got this x-axis and this y-axis. I'm going to have this kind of square rooty looking thing, this sideways parabola. And it's plus or minus, so I need both the top and the bottom right now. And then I have this line x equals 3. So I'm just going to kind of plop that in here. We'll call this 3. It doesn't need to be exact and precise. We just need to get a picture of it. And then it says this: the cross sections perpendicular to the x-axis are semicircular discs. So we're perpendicular to the x-axis and we are semicircular discs. So that means I'm going to have this semicircle right here. And everywhere I go, I'm going to have semicircles, and they're going to get smaller and smaller. And so remember, these little semicircles are pointing out at you. So it's like if you're looking at this, they are pointing straight up and out. So here's my dilemma. I need to find the formula for the area function. So I know that I'm going to integrate from 0 to 3. So at least that much is clear to me because I want to go from here. This is 0. And I know it is 0 because this point has the point 0, 0 on it, or this function does. So I already know that I can start setting up my integral from 0 to 3. So I've got that much down. So now I need my area function. So what is my area? All right. So we've made a sketch. We're going to determine a of x. We're a semicircle, so it's pi r squared over 2. So whatever the shape is, that's my area function. So the shape here is a of x, and so the radius, now this is tricky. I always have to look at my picture. The radius goes from the center of the circle out. So this is the radius. And anytime it goes from the x-axis up to the function, it's the function itself. So that distance from the x-axis to the curve is always f of x. So f of x, that's my radius. Well, what is f of x? It's this. This is f of x. Square root of 4x. Okay, so there's my function, okay, and that's my radius. So I'm going to go ahead and plop that in, pi, and then square root of 4x over 2, and then that's being squared. And this is dx. Now here's how I know that it's dx. And actually this is we should have talked about this before we even found a of x. Dx is always, you know that it's dx because as I look at my picture, the width of the cross section is a measurement along the x-axis. It's a change in x. So as you divvy up each cross section, you're divvying up the x-axis. That's how I know it's a dx, because that's the thickness of this semicircular three-dimensional little cut that I'm making. So it is a dx problem. Now here's the other thing. Wherever you're perpendicular to, if I'm perpendicular to the x-axis, that's an indicator that I'm going to set it up as a dx problem. So this is my integral, and now I'm ready to set it up and solve. And so let's go ahead and kind of evaluate this one by hand. 0 to 3, pi over 2. When I square this, I get 4x. So let's see, the 2, I get 2 pi x. 2 pi x, 0 to 3. There we go. So that's going to be 2 pi x squared over 2, evaluated from 0 to 3. The 2's cancel, so 9 pi, and then that'll be 0, so 9 pi. Yeah, there you go. So that area is just 9 pi. So let's keep looking. Let's see a couple more examples. Now this is an example that I love doing because it is very similar to something that we could see on the AP exam. And here we're provided with a graph, and so we know what the graph looks like. We know the intersection points. So we've got these two curves. We know which one is the square root of x. We know which one is the e function. And the cross section of the solid here are going to be isosceles right triangles. Ooh. So essentially the cross sections, oh, and this one did not say, we're going to assume that it is perpendicular to x-axis. That was I left that out. That's an error on my part. It will always tell you where you're perpendicular. So here's my picture, and when I sketch my right triangles, they're going to look like this. I'm going to have one leg here, and it's a perpendicular right triangle, or sorry, an isosceles right triangle. What that means is the two bases that form that right angle are going to be the same, which is nice. So there's one of my cross sections, and since I'm perpendicular to the x, this is going to be a dx setup. So now I need to know my area function. Well, the area of a triangle is 1/2 base times height. So what is my base and what is my height? Well, my base is this distance here. Now this is where it gets a little tricky because it's not going down to the x-axis, but rather it is a distance where it's this green curve minus this red curve. So let's talk a little bit about that. The green y would be this distance. So from the curve to the x-axis, is the green y, and from the curve, red curve to the x-axis is the red y, or the pink y. And so if you want what's left, if you want this distance here, you have to do a little bit of subtraction. You have to do the longer distance minus the pink distance. So the upper distance minus the lower distance. So here, the base of this triangle is going to be green y, and let's go ahead and label some things. We will label this y1 and y2. So it's going to be the green y, y2, minus y1. That's this distance here. Anytime you're going between two curves, it's the top curve minus the bottom curve. So that's my base, which also means it's my height, because it's an isosceles right triangle. So my area function looks like this: 1/2 y2 minus y1 squared, because it's that base times height, and they're the same value. So there's my area function. Now I'm ready to integrate. So I'm going to integrate from 0 to 0.7992, and it's going to be 1/2 y2 minus y1 dx. And I'm going to use my calculator to evaluate this one. Now as I type this one into my calculator, I have to be super careful about remembering the 1/2, but then also remembering to square my y2 minus y1, which I realize I did not write there. So when you type it in, and when you are looking at it, please understand that when you copy this down and you're squaring things, always write down what you're putting into your calculator for your AP exam and for your test, and anytime you're doing it, write it down. And then this is, look how ugly this is. This is why it's critical to put things into y1 and y2. That would have saved a lot of headache, because look at all those parentheses. It's so hard to keep track, and actually as I am creating this and typing it in, I am going back and spending extra time making sure it's typed in correctly, and so I feel good about this answer. But look at all those parentheses. Look how easy it is to lose track of what we're doing and what the answer will be. So 0.051 is our result here, rounded to 3 places. So this is how we want to do this setup. Is, you know, whatever we're perpendicular to, that's dx or dy. And we still need to see some dy setups here, but the idea is trying to figure out what's the dimension, what's the area, and our steps that we want to always follow are sketch a picture, decide if it's dx or dy, find an area function, and then set up our integral. So in terms of knowing if it's dx or dy, we would always look to see what are we perpendicular to. Are we perpendicular to the x-axis or the y-axis? And that's really going to tell us what our shape is going to be. Now to close this out, let's take a look at what I would consider to be one of the most difficult problems you might encounter. And for this problem, we're going to use the same two functions that we did, but this time we're going to make our cross sections perpendicular to the y-axis, which means it will be a dy setup, and I'll show you why in just a moment. But now we're also going to use semicircles instead of triangles. So we've seen squares, which if you can do a square, you can do a rectangle. We have seen isosceles right triangles, and we've seen semicircles, but now we're going to see a semicircle where it's just a little bit trickier. So let's take a look at what these cross sections are going to look like. Now we're perpendicular to the y-axis, which means my semicircles go like this. The reason why I know it's dy is because as I think about the width of this semicircle and think of it as kind of this two-dimensional shape, right? The width that I would measure, the thickness of that semicircle, is going to be a difference of the y. We're seeing the change in y. So this is why it's a dy type setup. So now let's take a look at what's happening. Now just like the last example, when I think about what my length involved here, if it's a semicircle, I know I'm going to use pi r squared over 2 because it's a semicircle. So to use pi r squared, I need to know the radius. Well, the radius here is this distance. And I have to be careful because it's not the entire way between the two curves, but rather half of it. So this is where it gets a little bit tricky. So In order to do a dy setup, we need to take our equations now and we need to solve them for x. So let's do that here. I've got, let's see, y equals square root of x. Let's do that one first. X is y squared. So that one's nice and easy. And then we have this other one. Y equals e to the x squared minus 1. So I'm going to have to add 1. And when I log both sides, I'm going to get x equals the square root of the natural log of y plus 1. And it's technically plus or minus, but because we're over here in quadrant 1 and its distance, we really don't need to worry about the minus. So really it has more to do with being distance than anything else. So we're going to use the plus, the positive version of this. So as I get it ready, when I set up my integral, to find my area function, it's going to look like this. My area function is going to be pi over 2, and then my radius. Okay, here we go. The radius is the distance between the two functions in terms of x, or in terms of y, really. So it is going to be the red curve, which over here is in pink or purple, minus the green curve. So this distance here is going to be, let's see if I can draw this in here. This distance here is the red curve, so it would be the square root of ln of y plus 1 minus y squared. So it's the same concept, but this time everything's in terms of y because it's a dy setup. But the radius is half of that. So if that's the full distance, the radius is this. Okay, this is where it gets tricky, right? I said this was the trickiest we would see. So here we go. The square root of ln y plus 1 minus y squared all over 2 squared. So everything gets squared, even the 2, because the radius is half of that distance, and you're squaring the entire radius. So let's just set up our integral. We're not going to evaluate it. I think just setting it up is pretty sufficient. So let's see what it looks like. When I set up my integral, I'm going to integrate from 0 to 0.894. So I have to go from y to y. Okay, so you have to use your y coordinate. So now it's the area function, so pi over 2 times the radius squared. So here we go. Make sure everything in the radius gets squared. Wrap the entire thing up. So pi over 2 radius squared dy. There's my setup. And if I punch that into my calculator, I should get the answer that I want. But the setup is where all the difficulty lies. And frankly, on your AP exam, a lot of times they ask you to set up but not evaluate the integral that would lead to the answer, because the setup is it's the hard part. And what makes this one tricky is, number one, it's dy, so we have to solve all of our equations for x equals to be able to use them. We need to remember to use our y coordinates when we're dy. And then what really made this one tricky is that the semicircles, instead of spanning the x-axis and being straddling an axis so that the radius was just the function, here we had to really do some critical thinking and understand that the distance between the two functions is function 1 minus function 2, but the radius is half of that because it's the radius of a circle. The entire thing would be the diameter. And then, of course, pi over 2 because it's a semicircle. So to kind of summarize everything that we've talked about here in this introduction to volume, remember, when you're trying to find the volume of any solid, whether it has a flat base or we will see soon, it may not have a flat base. It may be revolved around an axis. That is coming. But the idea is if you can find a function to represent the area of the cross section and you put that into the integral, remember this area, it's like when you have a little box, right, a three-dimensional box, or it could be a three-dimensional triangular box. The width of the box is your dx. The area function is the surface area. So when you're doing base times height for a box, that's your area function. It's your surface area. When you have a box that is made of a triangle, it's the same idea. So whether it is, this three-dimensional looking triangle thing, you have a base, you have a height, you have a dx, or sometimes if it's a function of y, it could be dy, depending on how it is laying on the function. But you have a base times a height, and so the area here is 1/2 base times height. Here, the area is base times height. If you have a circle, it's pi r squared. If it's a semicircle, it's pi r squared over 2. So you really have to kind of do some analyzing here and understand, is it rectangular, triangular, or semicircular? Those are the three most common bases that you'll see pop up in this class and on the AP exam. And if you can understand it's the area of a cross section in terms of x or y, depending on perpendicular to x, then you want everything in x. Perpendicular to y, then you want everything in y. If you can remember that, you can be really successful with these. And so just keep practicing. The more you do, the better you're going to get. You can do it. You've got this.